Hello, good afternoon. Welcome everybody to this second event of this series of Mixed Gen that we started last month and will be ongoing until the summer. We decided to start it because of the effect that pandemics is having in our ability to interact scientifically, and especially because of the impact that this is having on young researchers, on researchers at their earlier stages. And so we have created these events for an afternoon where we approach different areas of molecular modeling in a format that tries to, even taking into account the distance and all the limitations we have to face, try to keep the spirit of the interaction that is a feature of events organized by CCAM. So in this context, these events are structured in two parts. There is this first part where we invite an outstanding lecturer to provide more of a vision talk of the area. And also there is afterwards this poster session, and out of the poster that we have received, then there has been a selection of two younger speakers who then also can deliver a talk and interact with all of you. Today's topic is about active matter, and all the topics are already online, so you can go to the CCAM website and see which are the ones that will come later in the coming months. And I will also be happy if you can disseminate it either to people or other colleagues that are active in the corresponding area, or also young researchers who want to learn about other areas of molecular modeling as part of their training. So as I mentioned today, we have this session on active matter, and we have three speakers. We'll start with Julia Yeomans from the University of Oxford, and afterwards Bruno Venteju from COA in Chaclay, and Supriya Supriya Bajpai from IIT in Bombay. And I will ask all of the three speakers to try to keep in the time to ensure that we have organized it in a way that there is enough time to have also an as interactive as possible discussions. So let me briefly mention you how we are going to handle this first part of the event. Few technical points for all of us to understand how to behave. Well, first of all, this session will be recorded, and then it will also afterwards be available on the CCAM YouTube channel. For all of you attending this first part, the video is not activated. And then also for the chat feature of Zoom is deactivated, and this is done to facilitate the communication and to streamline it. So all the interaction that you will have during this first part will be carried out through the Q&A channel of the Zoom window session you are connected to. For the first lecture, the one by Julia, since this is a more extended talk, there is the possibility for you to ask questions during the talk. This is a bit of a challenge because we are all away from each other. In order to streamline the interaction during this part and do not stop too much the flow of Julia's talk, in this case, what I will ask you is that you write down the question you want to post during the presentation, and then I will be acting as a chairperson, and then will pass or tell Julia that there is a question, and then just pass the question to her. When she finishes the presentation, then we will have a devoted also part of the presentation for questions, and here you can ask the question yourself. So in this part, again, once the presentation is over, you can, using the same Q&A channel, there is no need for you to write down the complete question. You simply can say, I want to ask a question, and then you will receive a notification that's handled by the IT team saying that you have to unmute yourself. Then if you accept this request, then you will be able to talk and to directly address the speaker. For the other two talks, the one by Bruno and by Supriya, in this case, because they are shorter, we will sort of take care of all the questions at the end of their presentations. And again, that's done through this Q&A channel. And all you have to say is that you want to ask the question, and then we will be giving you access to tell you when you can pose the question directly. Okay, so in this sense, I think we hope to create an environment that is a bit more interactive and informal than having to write down the question during that part of the presentation. So that's, I hope it is clear how we should interact. And then without further delay, we can now move on. We can so say hello to Bruno, who had some technical problems. He's back now with us. So Julia, please, now the floor is yours for your presentation.
Thanks, Ignacio. Let's see if I can get it to work. Right. Okay. Just get the right thing there. Good. Well, thank you very much. It's really nice to talk to you. Good morning, good afternoon, or good evening to everyone out there. Thanks for joining. I really urge you, if I say anything wrong or don't explain things, please put questions in the question and answer thing, because it's always nice to know there really are people out there listening. I'm going to talk about phase field models for mechanobiology. And this is something we're reasonably new to. So putting this together into a talk was really to help me as much as to give a talk. I'm going to tell you where I'm up to so far in understanding this. And I'm really looking forward to people's input and to talking to people during the poster session, because I'm sure that this is a field which is going to evolve a lot in the next few years. So before I start, thank you very much, particularly to Armin, Guanming, and Roman, who are the people who've been on this journey with me understanding these things, and also a list of other people in my group who are now working on this, and experimentalists whose input has been absolutely vital to the way we think about this. So this is what I'm going to do. First of all, I'm going to talk about the sort of questions we're trying to answer, because I think some of you are sort of perhaps more traditional active matter people. A lot of people are doing lots of different bits of active matter. And so I want to talk about what I mean by confluent cell layers, and just summarize the sort of questions that are interesting at the moment. I'll then give a brief overview of the models that are out there and concentrate on then the phase field model, this particular one that I'm trying to think about at the moment. And then I'll talk about some things which I've learned as a result of thinking about the phase field model. I think we do have one or two answers, but still loads and loads of questions. So this is what I'm talking about. I'm talking about confluent cell layers. So two-dimensional layers of cells, which are usually moving around on a surface. And they don't just sit there. They're very much active. They're using energy from the environment to move around. And they move around in a fairly turbulent way. But if you look at longer times with this video, what they actually end up doing is somehow forming some sort of collective behavior and starting to move around in a circle. So what sort of questions are there? Well, first of all, presumably this is an active system. Can we model them as an active pneumatic? Is active pneumatics a sensible sort of model for cells? Active pneumatics are systems where you see something which looks like turbulence, which we call active turbulence. And certainly the velocity fields you can measure in the cells is very reminiscent of active turbulence. For example, you get large vortices and you get jets of strong velocity. And one of these is a simulation of a continuum active pneumatic model. and one is flow fields from cells, and I can't remember which is which because you can't tell the difference between them. The other thing which characterizes active matter is active topological defects, self-propelled topological defects. These are plus a half defects, which are the green ones, and minus a half, which are the red ones. And the plus a half defects move around because they've got energy from the active systems. And these defects have now been identified in many cell layers, and indeed in bacterial layers as well, in layers of bacteria. And so the question is, are they the same as you get in active pneumatic models? Certainly on the surface, they're certainly self-propelled topological defects. Can we just say they're exactly the same thing, or should we have different ways of thinking about them? And then there are also some beautiful recent experiments from the Paris group, where they looked at a cell layer in a channel and found that beyond a certain channel width, one started to get a shear flow in the channel. Spontaneously, one got a shear flow, and they're very pleased about that because in 2005, they predicted such a flow in channels of active matter. And what was happening in the cells and what was happening in the active systems very much matched each other. So there's certainly a lot of evidence that these things are starting to look like active pneumatics. So then another question. This is an experiment from Chicago, from Sally Horn-Badavinak's lab. And this is the egg chamber of Drosophila, and the eggs grow in the middle. And around the outside is a layer of cells. And these layer of cells don't just sit there, they move in a certain direction. Here's a movie looking down on that layer of cells, and you can see they do flocking essentially. They all move in the same direction. So then compare this. This is what I showed you before. This is MDCK cells on the surface. So we've got confluent cell layers moving in two different ways, flocking or not flocking. What determines which? What determines how these things move? And indeed, some unpublished work from this lab has some lovely experiments. When they stop the rotation, basically they send the cells to sleep, and then they start it again, and the cells take off in the opposite direction, and they keep doing that, and the direction keeps reversing each time. And that's probably physics as much as biology, and it'd be nice to be able to explain it. This is another very beautiful set of experiments which show the same sort of thing. This is from the Milan group. And what they found is that they started off with a confluent cell layer. So this is a cell layer doing active turbulence, like you sort of expect it to. And then they added RAB5A. And no one's quite sure what this does, but it probably mucks up the cell-cell junctions. And these cells just took off. They started flocking. These are the velocity vectors. They suddenly move with a huge velocity. So the blue curve says what's happened when you're doing active turbulence, the mean velocity. The red curve says what happens when you add this RAB5A. And for a biological experiment, this difference is amazing. I've got a movie of it in the next slide. On the left, we have active turbulence. On the right, these cells suddenly start flocking, possibly because you've done something to the cell-cell junctions. But we really can't understand what's going on there, certainly in terms of biochemistry and also in terms of physics. And then one final example, which I learned about very recently, is this wonderful stuff called ERK, which is a chemical you get in cells, which is thought to change the tension between cells. And it's not very obvious, but you can sort of see waves of ERK proceeding backwards as this cell layer expands. And at the same time, you can see, you use your imagination a lot, waves in density. And if you measure these more carefully than you can just see in the movie, you get a correlation between the waves in ERK, the chemical waves in the ERK activity, and the density waves in the cells. And so one's got a really nice mechanical, chemical coupling here. And that again is something which would be nice to be able to understand better. So those are the questions. Now, what about the sort of models you might have to look at these questions? And if anyone's interested, this is a very nice review, which summarizes very nicely the sort of models that are available. Well, first of all, what I'm most used to is these continuum models, active pneumatic models, active polar gels. And what these basically are differential equations, which you write down based on the symmetries of the problem you're considering. And I think that's very nice because you sort of know what you're doing. And so anything that comes out is rather generic, and you can link it back to the symmetries of the system you're looking at, and therefore apply it to many different systems. The problems with the continuum models are, first of all, that it is rather difficult to know what the parameters to match them quantitatively to experiment, because parameters, things like the viscosity, things like elastic constants, things like the strength of the activity are difficult to measure. The other problem is that sometimes there are more mesoscopic or microscopic features that are being missed out. For example, again, these cell-cell junctions are probably important, and it's not obvious how to put those into the continuum models. So you need to go down a bit in length scales, and perhaps the next thing would be the particle models. And in particular, the V-check model has been incredibly important in this field. It really started off the field of active matter. So what the V-check model does is that it's basically a set of particles moving around, which is self-propelled, active, and which align with each other. Their velocities align with each other with some sort of interaction. And there's also some noise which tends to disalign them. And I think we'll hear more about the details of that later. But in particular, you see a flocking transition. And so just very simple models can give you very generic features, and you can build on that to get more complicated systems. But cells probably, I mean, particles are all very well, and you can think of particles at the centers of cells, and that's got some way, but really cells have a shape to them. They have a sort of polygonal sort of shape. And therefore people have built on particle models to get Vertex and Voronoi models. And by these, I mean ones where the energies tend to be associated with the edges of the cell rather than the particles themselves. And for example, here we have a typical model of this sort, a Voronoi model, where you have a set of particles which represent the centers of the cells. By doing a Voronoi construction, which is basically bisecting the edges, you can get a shape of a thing which looks like a cell. And so this the red network looks like a confluent cell layer. And then you can associate some sort of energy, and you tend to associate energy, say, with the area of the cells, which have a preferred area, and then with the perimeter of the cells, the total length of the red line, which has a preferred length. And then if you want to make them active, you can add some sort of self-propulsion by a polar force, which can act on the black dots or perhaps on the cell vertices. And even this simple model has been very useful. In particular, it predicts a phase diagram looking pretty much like this, which gives a transition between a glass-like state where the cells don't move around much and a liquid-like state where they start moving around much more. So then what this perhaps doesn't do is look so closely at the properties of the intercellular connections. That probably a Voronoi connection is perhaps useful, but not so physical. So the phase field models try and build on that a little bit more. They're slightly more realistic, but on the other hand, you can't do so many cells. And so you can't go to such a large number of cells than you can here. So let me move on now to what I'm going to mainly talk about. And that's using a phase field model to model confluent cell layers. And the way I'm going to do it is to talk about the various forces that one might put in, starting with the passive forces, and up to here, it could be a load of bubbles, really. And then the various active forces. And I'm going to first of all think about polar active forces, and then I'll talk about dipolar active forces. And I think it's important to point out that what I'm saying isn't right. It's a best guess so far. So we can guess what these forces should look like. We can compare the results with what's happening in cells, and then we can go back and iterate and see what sort of model of cells is going to be most useful. I think it's quite important not just to get something which looks like cells, but something which can actually predict something new or help you understand something new. And so at the end, I hope I'm going to say, there's a long way to go, but there are a few things which we understand now, which we understood less well a year ago. So start with a movie. This is what the phase field does. It looks like a load of cells moving around. I dare say that to biologists, to physicists. I don't think biologists will think it looks like a load of cells, but it's the best we can do at the moment. So what's the algorithm behind this? Well, each cell is described by a phase field variable, phi I, which basically distinguishes the inside of the cell from the outside of the cell. And then phi I evolves according to an equation of motion like this. It evolves in time, it's convected with a velocity v, and it relaxes to the minimum of a free energy. And this v is related to the total force acting on the cells with some sort of friction coefficient. So the total force is just proportional to the velocity. Other way around, really, the velocity is proportional to the total force. So what's this free energy? What terms do we put in the free energy? And again, let me stress that, we're guessing. The first two you do need. This is the Cahn-Hilliard free energy, and this is what we're used to when we use a Landau expansion to describe a phase transition. There's a free energy here, which is minimized by two values of the variable phi. Phi can be 0 or 1. And so we have 1 being inside the cell and 0 being outside the cell. And then this term here is a gradient term. And this gradient term just imposes a surface tension between the inside of the cell and the outside of the cell. And so it defines a boundary. And the advantage of the phase field models is that the boundaries can move around on their own, just governed by the free energy. You don't have to put any extra boundary dynamics in. Then these cells have a certain size, and so we put on a Lagrange multiplier, which provides a constraint on the area, and it's a soft constraint on the area. And so we're doing a system which is compressible. Then you're guessing to some extent, but it makes sense that the cells don't want to sit on top of each other. And so one puts in some sort of repulsive interaction. And this repulsive interaction says that we don't want the phi's to be 1 in the same place. And so it stops the cells overlapping. But if it just had that term, they wouldn't form a confluent cell layer. They'd be going off all over the place. And so then one needs another term which favors adhesion between the cells. So this says that the interfaces like to overlap. When you see a grad phi, when this is non-zero, the gradient in phi is non-zero, you're at an interface. And so having this term here just says that the interfaces like to sit on top of each other. The sign is right because grad phi I for one cell and grad phi I for its neighbor are going to be in other opposite directions. And then once you've got a free energy, it's known how to define the resultant passive force. And you can do that. And up to now, we're really doing bubbles. And if we allow it to relax to equilibrium, what we'll get is just identical hexagons in the system if it actually manages to reach its ground state, but it can get stuck in a jammed state. Okay, so that's the passive forces in this system, but we're trying to model cells. So we'd like to model active forces. So how are we going to try and do that? Okay, so we know how cells move. This is a nice picture of a cell. They move by pushing actomyosin cables forwards. So these things push the front of the cell. And then they grab hold of the surface using these lamellopodia, which they push forwards. And then they pull themselves across the surface, essentially by putting a force on the surface. So they're pulling themselves forwards, forming these focal adhesions, so they're able to pull forward across the surface. So presumably there's some sort of polar force pulling the cell along. This is a physicist's version of that. You just get a single polar force pulling the cell along. And you need to put this in the algorithm. And you could decide to just put it at the front of the cell, or you could put it all the way over the cell just by deciding to put this force, just break it up so you had the same amount everywhere along the cell.
Sorry, Julia, before we move on into the active force part, there is a question by Rodrigo Soto on the equilibrium part that asks, why is it use a model A dynamics with a restriction instead of model B dynamics?
Nothing is conserved here. So I don't see why there should be model B dynamics. It's just, I mean, yeah, just because we don't have a conservation law.
Okay.
Yeah. Sorry, any others there?
So far, no, it's the only one. Just go on.
Yeah. Okay. So the active forces here. So these are the polar active forces which are pulling the cell along. And what we do is we define a vector in each cell, the polarization of each cell, and then just say that the force is proportional to the polarization. So that's really just moving the problem from defining a force to defining this vector P. And somehow we have to choose the polarization of the cell. And then we're guessing. So what we actually did is write down all the sensible guesses and see what difference it made. P could just be chosen randomly for each cell and then subject to some sort of Gaussian noise. Or we could have a V-check-like algorithm where P aligns with the velocity of the cell up to some noise. Or it could align with the long axis of the cell. Once the cell starts going in one direction, it wants to keep going in that direction. That's another possibility. And we're guessing, probably because we see flocking, maybe this is the most likely one, but certainly it isn't obvious. So we just have to put them in and see what might happen. We choose an alignment time. So this is how long it takes to align with something like the velocity of the cell, typically to be a time that the thing takes to move a cell diameter. And so far, we found that in fact the way you choose the polarization doesn't make very much difference, except for this number 2 here. This number 2 is the only case in which we got flocking. So let's just look at the phase diagram. This is the strength of that polar force. And at the moment, I've only talked about this bottom axis on the phase diagram. We'll come to this other axis in a minute. But along here, what do we see? Well, we see if the polar force is small, you get a glassy state. Basically, the whole thing is jammed. If you increase the polar force, you get unjamming, and you get a liquid-like state where the cells move relative to each other. If you have a system where you get this alignment with the velocity, a V-check-like algorithm, instead of just getting a liquid-like state, the cells will move off in the same direction and you get flocking. This says a little bit more about this jammed to liquid transition. This is the position of the centers of the cells. This is the jammed state, this is the glassy state, and this is the liquid state, and this is really how we're defining the difference between them. Things actually move more in the liquid state. And this picture here is really the same story. It's the rearrangement rate as a function of the strength of the polarization. Again, they get stuck. And then there's a crossover, not a sharp transition, but a crossover to this liquid state. And that very much is the same thing as is seen in the Voronoi and Vertex models. This is just another movie because this is what happens. This is how you actually get the things flocking. So we'll see this flocking. So this is when the polarization of the cells aligns with their velocity. So this is really just a fancy V-check model type setup. And you can see that this thing organizes itself so that you get into a state where you get everything flocking in the same direction eventually. Okay, so that's putting a polar force on these cells, but what else is going on here? Well, everyone says that cells are contractile, and indeed it's thought that, known perhaps, that back here in the back end of the cell, one has an actin-myosin machinery where myosin motors are sort of pulling on the actin filaments to contract them to help the end of the cell keep up. So you get a polar force pulling the cell along, and then you get a dipolar force, a stresslet, if you like, you use the math terms, which is restoring the cell to circular. It's trying to pull the cell back to being a circle. If you didn't have this red one here, these green ones would just pull it back to being a circle. So how would we put that into the algorithm? Well, what we do is we define a polarity tensor, which is just defined in terms of the polarization like this. And what that means is that the dipolar axis will lie parallel to the polarization. Once you've got a polarity tensor, this translates pretty much straight away into a stress. And then the force is just the divergence of this stress. So what's happening in pictures is that as the cell moves along, you have a polar force pulling it along, which is going to stretch it. Here I've got the polar force sitting at the front of the cell. And then we have a dipolar force density, which looks like this, which has forces like this and actually ones like that. And so you end up with this particular setup with the dipolar force density being distributed around the border of the cell. And that's going to tend to squish the cell back to circular. And so, I got a movie there? No. So as it moves along, it's going to end up being circular. And actually, that's a bit boring. And the reason it's a bit boring is that the surface tension will do that for you anyway. So if you turn this off, it will still do pretty much the same thing. It will just end up being a little bit more elongated because the surface tension is trying to squash it. But what is much less boring is forces due to the cell-cell junctions. So up to now, I've talked about a single cell, but what we want to worry about is actually cell layers. So let's think of a cell next to its neighbors, and let's worry about the cells between the cells, so the intercellular forces. These are going to be dipolar forces. The reason they're going to be dipolar forces is that the cells sort of are pulling on each other, so there's always going to be a force, an equal and opposite pair of forces. There's nothing external. For these forces, you're not putting on a substrate. So just like a swimmer has dipolar forces moving it along, so these intercellular interactions must be dipolar forces. They could either be extensile ones. By extensile, I mean that if the cell is elongated in this direction a little bit, the extensile forces will try and elongate it more in that direction and then squish it in this direction. So extensile forces will extend any deviation from circular. Contractile forces, it's a bit like we had before. If the thing is elongated in a given direction, the contractile forces are going to move so as to push it back to a nice circle. We think that the forces due to cell-cell junctions are probably usually extensile forces. I'm going to show you some evidence for that, but I think there's still some questions about if they are extensile, and I'm still thinking quite hard about why they might be extensile. So how do we put them in? Well, now what we want is that our dipolar interaction lies along the deformation of the cell. If the cell's extended in this direction, we want the dipolar axis here, and then we can either make our forces extensile or contractile. So we define a deformation tensor. So whereas before we had a big P, which defined our direction, here we've got a deformation tensor. It lies along the deformation of the cell. And then from that, we can get the dipolar stress and we can get the forces acting. This set of equations will give you a force distribution which looks like that. For the experts, this deformation tensor is essentially the same as the Q tensor that you use to describe liquid crystals. And the coarse-grained version of this stress is just the zeta Q that you normally get in the continuum model of active pneumatics. So what does it do for you, this dipolar interaction? So these two movies, this one just has a dipolar interaction, no polar force, just this dipolar one, just the interaction between the cells. Same there, but it's stronger. So what you expect is that this tends to elongate the cells, and that's exactly what happens. Strong dipolar interaction elongates the cells, and it makes it easier for them to move. Makes it much easier for them to move relative to each other. So now we can go back to the phase diagram and add this extra axis up here. This is the strength of the, should have changed that to dipolar, strength of the dipolar force. This is the strength of the intercellular interactions. Again, they can change you from a glassy state to a liquid. And the other thing they do is destroy the flocking state. So here's the flocking, and they destroy the flocking state. And this is again the rearrangement rate. This is the graph I had before. Dipolar interactions, just like polar ones, can get you from a glass to a liquid. They can make it easier for the cells to rearrange. And the transition is much sharper, for reasons I don't really understand, but the transition between the glassy state and the liquid state is much, much sharper. So this is the summary of the forces that I've put in the model so far. The passive force distinguishes different cells, and it basically sets up the model, and then it worries about adhesion between the cells. And so it's the passive part of junctions between cells. Then you have active forces. Certainly cells have a polar force, because else they wouldn't move at all, they just change shape. So you get the polar force pulling them along. And then you get a contractile force restoring them to circular. And you could put this in as a dipolar force or a stresslet, but it's not super important. It just sort of helps them get back to a circle. Probably much more interesting are the active forces due to cell-cell junctions. And these are probably extensile dipoles. And so if you get a small fluctuation which elongates a cell, what's going to happen is that this extensile force due to cell-cell interactions is going to pull it and is going to elongate it even further. That's where we're up to so far. This is the best guess at the moment. Just briefly talk about something else, which I think is going to be important and which we've started to put in the model, but not really got any results yet. And this is a thing called contact inhibition of locomotion. It was first written down ages ago by Abercrombie, who apparently was at Oxford, I discovered when I was looking him up. And the original paper said that if two cells come into contact, they really don't like each other. And like well socially distanced objects, they tend to move away from each other, and they like to come together. There's some sort of chemical signaling, and then they start and move away again. And you can easily put this in the model because you can get the polarization to point away from the direction of greatest cell-cell overlap. And then that's been extended, sort of almost by osmosis, I think, over the 50, 60 years since Abercrombie first put it down, to use the same ideas about what happens to cells inside a colony. Inside a colony, cells seem not to form lamellipodia. Occasionally you get things called cryptic lamellipodia, but they really don't want to form lamellipodia, which one might translate into not wanting to put a polar force in the model. And that suggests that really within a colony, maybe the dipolar forces are dominant. But it's really interesting, this contact inhibition of locomotion, because as far as I know, nobody really understands the biology behind it, and everybody believes it, but nobody is quite sure how and why it works. And putting it in the models might be an interesting thing to do. Okay, so we've done that. We've done the models. We've enjoyed writing these codes and things. Now let's think about questions we might ask. Can we say anything useful? So these are the three things that I want to talk about. First of all, flocking. Okay, so these are the experiments that I showed you, these very nice experiments. You start with an active turbulent-like state. You get rid of the cell-cell interactions, probably, but no one's quite sure what this does, but it probably weakens the cell-cell junctions. Weakening cell-cell junctions means that my zeta variable, the strength of my dipolar force, decreases. And so I move from a liquid-like state into a flocking state. So that at least can be explained by this way of thinking about things. Next, let me think about active pneumatics and topological defects. As we know, in active pneumatics, you get active topological defects. This is from the continuum model. Plus a half defects look like this. They get destroyed in pairs, and they also get created in pairs with plus a halves and minus a halves together. And these plus a halves are motile. They move. They move because they're gradients in the order parameter, and so they're stresses. The plus a half defects move in this direction in extensile systems, and they move in that direction in contractile systems, at least in the continuum models. They also set up flow fields. The flow field around a plus a half defect looks like this. The minus a half defects have this interesting six-fold flow field, but they don't move because the flow fields balance. These are the properties of topological defects we understand from continuum systems. Some time ago now, we looked at MDCK cell layer. Experiments were by Thuan Ben So and Benoit Ladu's group. And if you take the cells and you map them onto a pneumatic, okay, so they're circular cells. How do I map circular cells onto a pneumatic? Well, at least instantaneously, these things are pulled in a given direction. So at least they're pneumatic fluctuations. And so at least instantaneously, you can stick some sort of pneumatic direction, a pneumatic director on them. And what you find is topological defects. This thing here is a lovely plus a half topological defect. And it moves, which active topological defects are meant to do. And it moves in the direction that you expect an extensile defect to move. So this is one of the pieces of evidence which suggests that these cell layers are have extensile dipole interactions. And if you look at the velocity field around a topological defect, you can indeed see that you get an extensile sort of flow field around the defect.
Sorry, Julia, because before we go on, now that you are explaining the results, there is a question by Souzan Hamadi, who was asking the type of solver that you are using to for all the results you're showing.
We basically put this thing on a lattice and then solve it as a set of differential equations.
Okay.
Yeah. So it's not a CAN solver, it's one we've written ourselves. In particular, Romain Muller wrote it. And there's some clever things in it, which mean that you just have a stencil for each cell, which saves a lot of time. Mm-hmm. But it's a finite difference solver for the differential equations.
Okay, thank you.
Yeah. Okay. So, where was I? So we've got these topological defects moving around. Okay, so then the question is, you know, these cells are meant to be circular. I'm trying to describe them as an active pneumatic with active topological defects. Why can I do that? Why am I allowed to treat these as an active pneumatic? And the answer is very much this picture I had of cell-cell interactions. If I have extensile cell-cell interactions, what will happen that any small fluctuation is going to create dipolar flows, which pulls things outwards in this direction and pulls them inwards in that direction in an extensile system. And so you're going to get an increase in the pneumatic ordering. You're going to get a bootstrap-like effect, which this cell is going to get longer and longer, and it's going to tend to pull its neighbors in the same direction. And so you're going to get pneumatic ordering. And once you've got pneumatic ordering in an active system, you can start looking for active turbulence and topological defects. It only works if the system is extensile, because if it's contractile, exactly the opposite happens. what happens is that this axis is switched back to circular, and you don't get this bootstrapping of pneumatic order. This is hand waving. You can do it properly in the continuum models of active pneumatics. You see exactly the same thing happening, that even if you start with an isotropic state, shear flows in an active system can build up pneumatic order. And so you can get active turbulence even when you start with an isotropic state. But one of the questions I still have is that in the continuum models, it's shear flows which are formulating the pneumatic order. You can see it's shear that's lining up the pneumatics. Here, it's probably these intercellular interactions, but it might be something different. Just to show that in the models we can see this, we looked at, this is just results from the models where we don't show individual cells, but we look for topological defects. Well, we do that, yeah. Look for topological defects and look at the velocity and vorticity fields. And in particular, the vorticity field for the experts looks exactly like you'd expect from active turbulence. Okay, so this is my last slide, and this is some very recent experiments we've been involved in, but it's Lakshmi Balasubramanian, again in Benoit Ladou's group, who's done all the hard work in terms of the experiments. What I've been saying is that it's these extensile cell-cell interactions which give you active turbulence, and that they're due to interactions between the cells. Okay, so this is what happens in an MDCK cell layer. You get topological defects. Here's the flow around the topological defects, and the defect moves in this direction, and moving in that direction means that this is an extensile system. So I've claimed that the extensile forces come from cell-cell interactions. So let's try and make them weaker and see if the extensile forces go away, because the single cell forces were contractile. So by doing clever experiments, Lakshmi was able to weaken the cell-cell junctions, not completely destroy them, so we still had a cell-cell layer, but weaken them. And what happened was that she looked at the topological defects, and this is a typical velocity field around the topological defect looking like this. The defects started moving in this direction, and so they started looking like contractile topological defects. So that is my evidence that cell-cell interactions in these systems should be modeled as extensile dipoles. There's still a layer of question mark, a big layer of question mark, which says, okay, we can model them like that, but what's actually the underlying chemistry, the underlying biochemistry, which is causing these interactions between the cells? So that's what I've talked about. That's where we're up to. As you can see, it just about hangs together as a story, but there are lots and lots of questions still to be answered. I look forward to seeing everybody's posters, because I guess you're the guys who are doing a lot of the answering. Thank you very much for listening.
Okay, thank you very much, Julia, also for staying in time. So we have now quite an amount of time to have a more lively discussion. As I mentioned at the beginning, for those of you who have been joining later, you can post the only communication channel is through the Q&A window that you have. And it is enough that you indicate that you want to ask the question. Then you will receive a note asking you to unmute. And then if you accept it, you will have access to the mic. then I will tell when you can pose the question. So please, you can simply indicate in the channel, I want to ask a question, and then some of the questions that you can elaborate and then interact more directly with the speaker, with Julia. So we have already two questions. First one is by Chaitanya. So please, if you want to ask the question.
Hello, am I audible?
Yes.
Yep.
Thanks for the interesting talk, Professor Julia. I have a question related to the first part of the talk. So in the experiments that you have shown, all the cells have a nucleus. Right? These are all nucleated cells, and the nucleus itself can deform and generate its own dipolar stress. Right? But so do you think accounting for that dipolar stress within the cell and the interaction of that stress with the inner wall of the cell, interaction of the dipolar stress of the nucleus with the inner wall of the cell may better the understanding of these systems?
So what's your evidence that the nucleus is acting as a dipole?
No, because the nucleus can deform, and so because it's not like a rigid object which can deform, so that's why I thought whether it may generate this stress field. But I don't know whether.
Yeah, I mean, I think there's an awful lot of signaling that goes from the nucleus, between the nucleus and the cell wall, which I don't really know very much about. And I don't understand quite why that should particularly be a dipole, but it's one of the extra layers of biology that we're just completely missing out here. And we just have to try and work out what's going to be, important things to put in next.
Okay. Thank you.
Thank you.
Thank you very much. So there's the next question by Carlo Massimo Casciola.
Yes, so I have a question concerning the numerical side of your talk. So you were explaining that you have a different field for each cell. So I was wondering which is the typical size of simulation that you can run. So what is actually limiting that? Because if I understood correctly, you are sort of localizing the description of each field, right? So can you say more about that?
Yeah, I mean, we can get up to 100 cells is easy, 400 cells is doable. But what you don't want to do is end up solving these equations for all fields everywhere in your simulation box, because obviously you have things +1 near a cell and it goes to 0 quite a little way away. And so you have to be careful about putting a stencil around each cell, because that speeds it up quite a lot.
Okay, thank you.
Okay, thank you very much. So we have then another question by Roberto Cervino.
Hi, Julia. Hi, Ignacio.
Hi, well, you're the expert, so you can tell me what I said wrong about your nice experiments.
No, I mean, it was a great talk. I really liked it. And I mean, as we also briefly discussed by email, I will be very much interested in understanding. I mean, now we have two models that explain well the unjamming transition that we observe in the experiments via flocking. Now, in our model, which is the self-propelled Voronoi that you introduced briefly at the beginning of your talk, the two variables that we mainly think are relevant are the alignment efficiency and the P0, the ratio between the target perimeter and the square root of the target area. Now, we think that, in our experiments, we see that both of them, or let's put it in another way, we interpret with the simulation our experiments by saying that the alignment efficiency, which is the inverse of your alignment time, goes up. So of course, cells realign more efficiently. They take less time in aligning more efficiently in aligning.
Yep.
And the other one is the P0 that goes up, which encodes the competition between cell-cell adhesion and cortical tension. So in the experiments, we see that both increase. So there is an increase in both cortical tension, so basically the surface tension of each cell if it were alone, and cell-cell adhesion. But of course, we conclude that cell-cell adhesion has to increase more because we see flocking. Now, your model focuses on different looks at the problem from a different angle. And I would be very much interested in knowing your opinion on what could be a mapping of the two models in explaining the experiments. Because in your phase diagram, you kept the time constant, right?
The alignment
So
time.
you didn't, yeah, the alignment time constant. Why we had to change it to explain flocking? So this is already a first difference that I can see. But maybe you can comment a little bit more about that.
Okay, so we had instead changed the strength of the interaction. And I'd have to go back and look at the results. But we do have results of how the alignment time changed it. I mean, my guess is the alignment time is important. The other thing we have is adhesion, and adhesion does make a difference. We have a parameter which essentially is the adhesion between cells, which I think is like your perimeter energy. Yeah. So, I mean, I suspect the physics is essentially the same. It's V-check physics that we're doing here. But it would be nice to compare the two stories. Yep, we can, I mean, we can certainly do that.
Mm-hmm.
Thank you. Thank you very much.
Okay, thank you very much. So the next question is by Patrick Warren.
Hi, Julia.
Hi, Patrick.
This might be just a dumb question, but in these phase field models, what stops the cells breaking apart into more than one piece, for instance? Is it just surface tension?
Yeah, you've got surface tension. You've got a Landau-like free energy. So you've got phi squared into 1 minus phi squared and then a grad phi squared term.
Just relying on that.
So it's just the normal phase separation story.
Okay, I had one other quick question, which is when you show these diagrams where you have the outlines of the cells in these phase field models, that must be some kind of level cut.
Right, that's at phi is a half.
Phi is a half, okay.
But it's a bit irrelevant, you know, that's just a choice.
Yeah, I did wonder, because obviously if you make it too low, then they all start overlapping.
Yeah.
Okay, that was it. Thank you.
Thank you very much. So then next question is by Giovanni Cicotti. Giovanni?
Here I am. Hi, Julia.
Hello.
You are working with fields.
Yep.
And I am curious how complex is this solution for you, numerically, I mean, numerical solution, I imagine. And if with your models you arrive to need really HPC, or you can do this computation in relatively standard way?
We're doing it, I mean, certainly for 100 cells, we can sort of do it locally on our local cluster without too much trouble. You can maybe run the things for about 2 or 3 hours.
So you have not to go.
So we're not doing
very much on the continuum problem. You can discretize, they are smooth enough, etc., etc. And the algorithm is ignorance is motivating my question. It's no more than that. And you use a trivial algorithm, or you need something a bit performant in the sense that there are instability. Is anything because in the continuum you can have a lot of surprises, as we well know, right?
Yes, yeah. That's right. I mean, it's not trivial, because you have to get ranges of parameters where things work sensibly. So it's not a beautiful, anything will go sort of algorithm, but it's not too bad.
No, but I mean, it's something intuitively you discretize the derivatives, etc., and you do by steps trivially, or you have to go to higher order and to use some specific tricks. It's really only curiosity. I mean, I don't know if you.
We use standard discretizations of derivatives. Really, because the things we don't understand are much worse than the sort of computational errors at the moment.
And it's complex to find a range, a numerical range for the steps, so that you don't lose the phenomena, because that's the problem of the continuum normally.
I mean,
you can convert.
You're better asking my graduate students than me, actually, for that. But you don't have to tune it very accurately to get sensible things.
So you don't lose specific phenomena easily. I mean,
yeah, I think that's true. I mean, it's probably not as robust as MD would be, but it's reasonably robust.
So it's not much more complex than, say, the most elementary standard molecular dynamics. Only now you're treating with continuum. I'm asking again. I have a good experience with MD, miserable experience with continuum. That's why I'm asking.
Okay. It's probably in between the two, I think, is the answer.
Okay. Okay. Thank you.
Okay, thank you. So there is a second question also by Zozan Hamadi.
Yes. Can you hear me?
Yeah.
Yeah. Hello.
Yes. Perfect. Hello. So I'm quite interested in phase field, and I've been working with it for metallic systems. So it's originally used for example, solidification in metallurgy. So it's quite interesting to see a different application of phase field. And I was wondering, maybe you already mentioned it, but how do you initialize the system? So at T0 at the beginning, how does the forces look like inside the cells?
To initialize it, we have to put cells in, right?
Exactly.
I think the answer is that we put them in with radius r/2 and then gradually let them grow till they touch each other.
Okay.
And then start with random forces.
Yes. Okay. Yeah. Sounds what I thought it would be. And then just a super fast question as well, because so in, for example, metallic systems, we use phase diagrams or like thermodynamics to differentiate between the phases. So now you have this inside the cell phase and then the outside. But what you do is you have this strength and that determine if you're inside the cell or outside the cell, I guess. So this.
I'm not sure I heard that, but this field phi is 1 inside the cell and 0 outside, and it's a different field for every cell.
Exactly, and it's connected to the phase diagram of the forces.
No, I don't think so.
Okay, because okay, but maybe I'm just confused because, for example, in conventional phase field, these phi equals 1 or 0 is usually connected to a phase diagram, so it would determine if we have maybe phase alpha or phase beta.
Yeah, okay, so the phases we'd have there are cell or not cell.
Exactly, yeah.
But when I plot a phase diagram, which is actually a bad term because it's not equilibrium, I'm doing it strength of force versus dynamical behavior.
Yeah, okay.
So it's a slightly different.
It's slightly different, yeah. Thank you so much.
Okay, I remind you that if you have the question, you simply indicate in the Q&A that you want to ask the question. I have a question myself now. I mean, it's partly related to the discussion you had with Roberto, but in retrospect, I mean, you started at the beginning talking about these phase field models with respect to Voronoi or particle-based models. At the end, once you have been explaining the mechanisms that you think that are behind this type of big check type physics, in which sense, or what do you think that these phase field models add that is qualitatively different from what you could get with a Voronoi or with a particle base, where you don't have possibility to handle deformation, but you could introduce the symmetry of the interactions among effective particles?
I mean, I think that the dipolar forces and its relation to cell shape is perhaps easier to think about in terms of the phase field. And that's the way we got to thinking in those sorts of directions. But having thought about it, you could probably then go back and put it into a Voronoi model and see. The big advantage of the Voronoi type models is that they're much quicker. So you can do lots more cells. And I suspect I've got used to the phase field models. When I first started with them, I was sort of thinking, oh God, you know, it's not anything like reality, but you sort of get used to it when you're doing it. So I'm not sure they're better, they're just a bit different and maybe help you to think about things in different ways. It's slightly more real, the interaction between cells, but but it still isn't perfectly real, of course.
Okay. So I do not see any additional questions coming up. I would like to remind that for those who have registered, we have the second part in this gather. We'll have the posters. That also gives the opportunity to informally meet each other. So you can also try to meet with Julia if you have additional points that you want to raise. So Julia, thank you very much again for this illuminating talk and for the discussion around it. And I hope you can stay with us, and then we'll move now to the next talk. That's by Bruno Benteju from COA in Saclay. And as I mentioned, given that the talk by Bruno and the following one by Supriya are a bit shorter, I would ask you to indicate in the Q&A if you want to make a question, and then we will handle them together at the end of the presentations. So please, Bruno, now the floor is yours.
Okay. Okay, is it working or?
We still see your screen now. Now we see the presentation. Yeah.
Okay, so my name is Bruno Benteju. I'm a PhD student and I work under the direction of Hugues Chaté. So I will present my work about Vic-Check model with chirality disorder. So first, let me introduce the Vic-Check model and summarize the result. So the Vic-Check model is a good description for a specific kind of active matter. This active matter system needs to be dry. It means that there is no interaction between particle and the surrounding fluid. You need to have only alignment interaction. It means that there is no repulsion between particles. And you need an homogeneous system, so identical particle with constant speed and evolving in an homogeneous space. So we will study the effect of a chiral disorder, and the main question is how robust are its collective properties, or in other words, how does the chirality affect the different phase of the Vic-Check model? So I want to say that some people have already considered this topic. We can cite Lewis and Lipschen, and Denk and Fry. So here there are the equation for the Vic-Check model. So the first equation corresponds to the self-propulsion. We can see that all the particles are moving at a constant speed v0. And the second equation is for predicting the polarization angle. We can see that there is two terms. The first term is the rotational noise, where with the amplitude dr, and the second term is the alignment term, where you can see that a particle will align with the neighbor in a disk of radius 1 here, and the strain is given by kappa. So here we can see that kappa and dr will play a symmetric role. In the Vic-Check model, there is 3 parameters. So there is the density, the noise, and the strain of the alignment. So because kappa and dr are playing a symmetric role, we will restrict the study to the fast plane density noise. Then we see that there is an alignment. So if the alignment is strong, we should get a synchronization of the polarization. It means that it should give a collective moment. So let's have a look on the phase diagram. So here I plot the phase diagram of the Vic-Check model. So for very high noise, we see that we get a disordered gas. And for very low noise, we see that we get polar liquid. But between these two phases, there is a coexistence phase where there is a bond phase. So on the top right, I show you a snapshot of a system in the polar liquid phase. So here you see that I represent the coarse grain polarization angle. So you see that all the particles are moving in the same direction because all the particles get the same color. So we see that we get an ordered phase. On the bottom right, I plot a snapshot of the bond phase. So here you see that all the particles inside the bond get the same polarization angle. So it means that all the particles are moving in the same direction. And outside the bond, we see that there is a disordered gas. So the liquid and the bond phase are globally synchronized and give rise to long-range polar order. So now let's say how robust are the ordered phase of the Wilczek model to the presence of chirality disorder. So here we see that we get the equation of our Kuramoto-Wilczek model. It's exactly the same equation from the Wilczek model, but we add an intrinsic chirality for each particle. So we call it a Kuramoto-Wilczek model because this is a Wilczek model plus a chirality disorder. Or if we forget the first equation, we get a Kuramoto model, which is a minimal model for the synchronization of oscillator, plus the first equation, which is self-propulsion. So now the question is, how can we draw the intrinsic chirality? So the chirality has been drawn with two different zero mean distributions. The first one is a Gaussian distribution with the width omega 0. And the second one is a bimodal distribution. So we have studied the second distribution mainly for analytical reasons. So these two distributions will introduce a new parameter, omega 0. But if you remember the phase diagram of the Wilczek model, we can see that the nature of the transition will not change with the density. It's only the value where the transition occurs will change. So we will restrict the study to the plane chirality noise, and we will fix the density. So let me present the result for the Gaussian distribution. So here you can see a phase diagram for the Gaussian distribution. So it's in the plane chirality noise. Each point corresponds to a simulation. You can see in the red hatch area the area where there is a strong finite size effect, and we work at a given system size. So on the low chirality, for the low chirality value, we see that there is a Wilczek model, so we get the disorder, then the bond, then the polar liquid. So now let me increase the chirality, and we see that at a given point we get a new phase which is called vortices. So for both bonds and polar liquid. So let me characterize this new phase. So here I show you a snapshot of a system in the vortices phase. So if we look at the right plot, we see that there is two packets, one blue packet and one white packet. So in this plot, I plot the coarse grain chirality. So it means that the blue packet corresponds to a packet with a lot of particles with negative chirality, and the red packet, a packet with positive chirality. So we see first that there is a segregation between positive and between particles with positive chirality and particles with negative chirality. Now let's have a look on the nature of the packet. So if we go to the coarse grain polarization angle, we see that the polarization inside a packet is turning around the center. It means that this is a vortex. So we get a vortex for the blue particle, so for particle with minus chirality, and a vortex for particle with positive chirality. So this is why we call the phase vortices. So up to now we have worked at a fixed system size. So we did an asymptotic study with the system size to see how we'll evolve the transition. So all the previous results have been done at the system size 128, so this line. Here we have fixed the noise at a transition between polar liquid and vortices, and we have changed the system size. We can see that when we increase the system size, the value where the transition, the value of chirality where the transition occur, will decrease as a power law. It means that in the limit of infinite system, there is no polar liquid phase. So now let's have a look on the transition at a noise where there is a bond vortex transition. We see here that the value where the transition occurs is not affected by the system size, but for above a given system size, we get an hatch green area, which corresponds to a coexistence between bond and vortices. So when there is enough particle, enough space in the system, there is a coexistence between bonds and vortices. So let's summarize the result. We have seen that the Kuromoto-Wilczek model provides a segregation between particles with positive and negative chirality. There is a new phase, which is a vortices phase. The liquid phase does not exist at infinite system size due to the chirality disorder, and the bond phase exists at infinite system size. Now the question is how to build a continuous field theory for the Kuromoto-Wilczek model. In fact, it's really difficult to do with the Gaussian distribution, but it's feasible with the bimodal distribution. So first, we will check the consistency of the result of the bimodal distribution with the result of the Gaussian distribution, and then we will derive the hydrodynamic equation for the Kuromoto-Wilczek model. So let me show you the result of the bimodal distribution. So we plot the same kind of phase diagram. At low chirality, we get the Wilczek model. Then we increase the chirality, and we get the vortices. So we get the same phase as the previous distribution. But when we continue to increase the chirality, we get a new phase, which is called rotating packet. So let me characterize this rotating packet phase. So here I plot the coarse-grained chirality. We see that there is a packet with blue particle and packet with red particle. It means that there is segregation between particle with positive chirality and particle with negative chirality. Now the question is, what is the nature of this packet? So if you take one packet, for instance, you can see that all the polarization are the same inside the packet. So it means that it is ordered. And now the question is, how does the polarization evolve in time? And if we look at the time series of the polarization inside one packet, we can see that one packet, the trajectory of one packet will be a cycle. So it means that the packets are rotating in time, and that's why we call this phase rotating packet. So we have seen that there is still a segregation between particles with positive and negative chirality. We get the vortices phase, but for the bimodal distribution, we get one new phase. So then we do the asymptotic study. Here I plot the same kind of phase diagram. We see that the limit between polar liquid and vortices decrease with the system size as a power law, but the limit between vortices and rotating packets is stabilizing with the system size, but the hatch area corresponds to a coexistence between vortices and rotating packets. So this hatch area is growing with the system size. So we see that here it's also consistent with the Gaussian distribution, because we don't get a polar liquid phase at the limit of infinite system size. So we do the same at the bound vortices level. Here we see that above a given system size, there is also the coexistence between bound and vortices, and the transition, the value where the transition occurs doesn't change with the system size. For the transition between vortices and rotating packet, it is the same, but the area of coexistence is growing with the system size. So we have seen that we get a consistency result between the bimodal distribution and Gaussian distribution. So now let's try to build a continuous field description for the Kuramoto model and try to investigate how it fits to the particle level results. So we will do the derivation of the hydrodynamic equation. So first, let me denote by F the one-body probability density function for the population with plus chirality, with plus omega 0 chirality, and by G the one-body probability density function for population with minus omega 0 chirality. So here I write two coupled Boltzmann equation. In fact, there is only one equation because if you want the equation for G, you can just exchange F by G and replace omega 0 by minus omega 0. So in this Boltzmann equation, you can see that there is one new term compared to the standard Vic-Check model. This new term is due to the chirality. So I highlight it in red, and I highlight also the cross term in orange. So I follow the Ginzburg-Landau approach to get the hydrodynamic equation. So let me define the angular Fourier mode. Then if we apply this transformation to the previous equation, it becomes this equation, number 7, where we can continue to track the new term due to chirality and the cross term due to the interaction between the two populations. Let me just tell you something about the angular Fourier mode. There is two particular angular Fourier modes. So Fk for k equals 0 is corresponding to the density field, and Fk for k equal 1 is corresponding to the momentum freedom. So now we continue to follow the Ginzburg-Landau approach by doing the truncation and closure, and we get the system of hydrodynamic equation. We get 4 coupled equations. So the two first equations are equations for the density field. So we get a conservation equation for the first density field and a conservation for the second density field, for the density field of the second population. And then we get the equation for the momentum field here. So we write in black the standard Tenor-2 equation for the Vic-Check model. In fact, there is a difference because here all the coefficients are complex, and in the standard Tenor-2 Vic-Check equation, all the coefficients are real. And in blue, we write the contribution from the other field. You have the same shape as the Tenor-2 equation. And in orange, we continue to highlight the cross term. So now we want to study this hydrodynamic equation. So first, we will try to find the homogeneous solution and study the linear stability of the homogeneous solution. So first, let me introduce the two homogeneous solutions. So there is two solutions. The trivial one is the disorder solution, and there is a non-trivial solution, homogeneous solution, which is corresponding to the polar liquid solution. In fact, we are not able to compute analytically the F1 and big omega for the polar liquid solution, but it's really easy to solve numerically. So now we will study the linear stability of the polar liquid solution. So in this plot, you can see a red line. So below this red line, it corresponds to the disorder solution, where the disorder solution is stable, and above the red line, the disorder solution is unstable. So we plot the characterization of the most unstable mode of the polar liquid solution. So we plot in the chirality density plane. Here we see that there is a gray area. The gray area corresponds to the non-existence of the solution of the polar liquid solution. Here, if we are in the area of the existence of the polar liquid solution, we see that we plot the growth rate, and the growth rate is always positive. So it means that the polar liquid solution is unstable everywhere. So we also characterize the instability by plotting the modulus of the vector. So it gives the scale on which the instability will develop and the direction. So, but the main result is that the growth rate is non-zero everywhere. So the polar liquid is unstable everywhere. And this is in a qualitative agreement with the particle level result. So let me summarize the result of the Kuramoto-Vicek model. So we have seen that the chirality disorder leads to two new phases: the vortices and the rotating packets. The liquid phase does not exist at infinite system size, and the bond phase is robust against the chirality disorder. Then we derive an hydrodynamic description of the Kuramoto-Vicek model, and we get a qualitative agreement between this description and the microscopic result. Okay, so thank you for your attention.
Okay, hello. Thank you very much, Bruno, for this presentation. And now we have some time for questions. I remind you, you can pose the question simply by indicating in the Q&A window that you want to ask a question. Okay, I don't see any question yet. So I had a curiosity though, Bruno, in the results you showed, you mentioned that this the polar liquid is unstable and disappears when you go to these large enough system sizes. However, in the plot that you were showing, that was as a function of this intrinsic rotational frequency, or the chiral frequency. If you take the limit of the frequency to 0, in that case, you should sort of like go back to the Vicek model. So I was wondering what happens in that limit to very small frequencies.
So we did some simulation computation with very low chirality, but it's not continuous with the Vicek model. So when we just add even a very, very low chirality, it breaks the polar liquid, the standard polar liquid phase, and we get this.
And that is the same also in the hydrodynamic when you derive the hydrodynamic.
Yeah. I did. I don't have the result here, but I just go to the limit at very, very low chirality, and we get a discontinuous limit.
There is also a question by Juan David Torrenegra.
Sí.
Sí. Yeah.
¿Sí me escuchan?
We can hear you, yes.
Okay. First of all, nice work. You consider any interaction between the swimmers in your model, like hydrodynamic interactions or effective volume interactions?
You mean in the model of so in the Kuramoto-Vicek model, there is no interaction. The only interaction is the alignment interaction. And then we follow the Ginzburg-Landau approach to get the hydrodynamic equation. I'm not sure to understand the question.
Okay.
Because there is two populations, and they align with the same okay, let me. So here, this is the microscopic equation, and you see that they are aligning with the neighbor in the vicinity. So it doesn't depend on what the chirality of the particle for aligning.
Okay. I forgot to mention at the introduction that because the presentation by Bruno and Supriya correspond to posters that had been submitted, those posters are also available in the Gather session, so you can further discuss with them if you want in the second part of the session. There is another question by Holger Stark. Holger?
Yes, hello, I'm Holger Stark from Berlin. I have a question. Do you have any realization in mind? Let's say in biology, you put some, or you chose some racemic mixture of left turning and right turning active particles or microorganisms. Do you think of any realization?
So there is a several realization that sorry, I want to move. So Denk and Fry characterize one situation where there is some curved polymer where forming some vortices and rotating packets and stuff like that. So this is with polymer, and there is also example with bacteria, but I don't get the reference here, but I can give you later maybe.
Okay, thank you.
Right, thank you. I don't see additional questions. As I mentioned, you can follow up the discussion with Bruno during the poster session. So thank you, Bruno, for this presentation. And then now we can move to the third presentation of this first part of today's session. And that's the talk by Supriya Bajpai from IIT Bombay. So please, Supriya, now the floor is yours.
Okay.
So you can start. And, it's coming up. Yeah, perfect.
So first of all, I would like to thank the organizers for giving me the opportunity to present at the mixed Gen event on the topic how the cell motility and the polarity controls the not signaling pathways patterns in the active tissues. So morphogenesis is the process that controls the organized spatial distribution of the cells. So in the figure, the lung morphogenesis is shown, and with the lung, and this morphogenesis is controlled by the signaling pathways and the cell mechanics and motility when they work in a coordinated way. So not signaling is one of the 7 or 8 pathways that govern centrally the embryonic morphogenesis, ranging from flies to humans. So not signaling affects multiple events as well as the multiple development events like the cell differentiation, cell movement, and the cell shape and size, etc. So in the figure shows the cell pattern or the differentiated cell patterns on the body of the fish with 2 different types of cells. One is the blue color cells and the other is the blue yellow pigmented cells, which have 2 different characteristics. So in biology, in the last couple of decades, we have gained a lot of information on how the molecules, proteins, and genes interact at the cellular level. And we are able to draw the detailed circuit of how these molecular interactions takes place. But we don't understand how these molecular interactions give rise to the developmental patterns, such as the differentiated cell patterns, as we can see in the figures. Also, during the development experiments, the development experiments show that the cells are in the motion during the patterning process. And we don't know how the cell movement and the signaling pathways coordinate to form such developmental patterns. Now we'll see how this delta notch signaling works. So in this figure, these are the two cells that is gray in color, and each cell has some notch protein and the delta protein. Here each cell has a delta protein as well as the notch protein. So, and these two, when these two cells come in contact with each other, they the notch protein of one cell binds with the delta protein of the other cell, and some cleavage action takes place, and it goes and activates the genes inside the nucleus, which makes the one cell say of X type and the other of Y type. So for example, one cell can become, suppose, lung cell, and the other can become the heart cell, or the one cell can take the red pigmentation, or the other cell can take the yellow pigmentation, like that. So delta notch is a transmembrane signaling protein, and the delta notch signaling is a contact dependent intercellular signaling. So it depends on the contact between the two cells, and the process by which this signaling takes place is the lateral inhibition mechanism. So cells are in contact, can be in contact with two methods. One is by the cell-cell junction, means the cells sharing the membranes can contact each other, and the other is via the cell protrusion. So here the cells through a spike-like structures in order to contact the cell at some far away distance. So this is these structures are known as cell protrusions. In this way, they can make the contact. So the cell fate or the cell differentiation mechanism takes place by the lateral cell fate differentiation takes place by the lateral inhibition mechanism. So in the figure, initially we see all the cells are of the same type. Then this lateral inhibition mechanism takes place, and few cells become this cell become the nerve cell, and other becomes the epithelial cell. So the delta protein of this cell binds with the notch protein of the cell that is in contact, and then the cleavage action takes place, and the cell achieves a different fate. Now the question arises, how do the cellular level interactions of signaling proteins and cell polarity and cell motility leads to the spatial pattern of the differentiated cells in the tissues? So the tissue monolayer can be modeled as the network of polygons with edges and vertices. Each cell has a cell perimeter, preferred area and preferred perimeter, and each cell has some delta protein as well as the notch protein. And the forces on the cell are assumed to act as the vertices. Now we discuss a very important term which is used in our model, that is cell polarity. This is an internal variable modeled as a unit vector and represented by the tangent angle of the polarity. So in reality, its dynamics is complex, but in our model, the cell polarity dynamics is governed mainly by the two parameters. First one is the alignment strength, that will try to align the polarity of the cell with the polarity of the neighboring cells. And the second is the rotational noise. This term tries to introduce randomness in the system. So the tissue polarity dynamics depend on the ratio of the xi and zeta term. If xi dominates, if this dominates, then this system will show an aligned behavior, and if this rotational noise term this dominates, then the system will behave will show very random polarity. And this is the polarity strength ratio. This is a number defined by xi and dr term, which we will look later on how this ratio controls the pattern formation in the tissues. Now this is the cell protrusion, and we model it by using mainly 3 parameters. So this red color is the cell, and this is the gray color area is the protrusions. So and this is the L is the protrusion length, P is the cell polarity, and we assume that the protrusions are oriented in the direction of the cell polarity. So and this is the angular range of protrusion, means all the protrusions of a cell will lie within this gray region, in the region of 2 delta theta. So here the delta notch kinetics is governed by 2 ODEs, where capital N and capital D are the delta and notch activity within the cell. D bar is the weighted average of the delta over the cells in the contact. So the cell can make contact in 2 ways. That is, one is the junctional and other is the protrusional. So these are the two contributions. And this weight term decides whether the cell will make contact or not. This is a weighted. This weight is given for to decide the contact between the cells. So these 2 profiles here are in this profile we can see that the cells, when they are coaxial in the nature, so they will establish contact with each other, and so the weight given will be very high. And if this is the configuration, then we can see that the protrusions don't make any contact. So if if it takes this configuration, then this weight will be very low, and it is decided that the cell will not make any contribution to this D bar alpha term. So the cell mechanics and the cell motility is also modeled in our system. The evolution equation of this vertex I is given by this equation: elastic force and the active force, where it has the viscosity of the overdamped system, and the elastic force is given by this equation, where U is the total free energy of the system, and the first term comes the first energy term comes from the deformation energy, and the second term comes from the membrane surface energy, and the third one is the cell adhesion energy, means the line tension energy. And this is the active force. Active force also acts on the cell vertices, and it acts in the direction of the cell polarity, and V naught is the motility, that is the magnitude of the velocity of the cell motion. The cells also show the topological rearrangements. So first one, we will discuss two of them. First one is the neighbor exchange process, or the T1 transition, in which we can see the 2 cells which are neighbors of each other, sharing a pink color bond between them. And then this T1 transition takes place in such a way, and then finally these 2 white cells which were neighbor of each other, now they are no more neighbors. Now the new neighbors have emerged, yellow and green color sharing this blue color bond. So the second topological rearrangement process is the cell death process, when this takes place when the area of the cell becomes very small, that is smaller than some threshold value. Then the cell is extruded out of the system and it takes this configuration. So our model is controlled by many parameters, but we will focus in this presentation. I'll focus mainly on these 2 parameters. That is, one number is the xi by dr, that is the polarity strength ratio. This will decide whether the system flows as a flock behavior, or in the aligned behavior, means in the same direction, or it will show the random behavior. And the cell motility term, second one. So now the how this xi by dr affects the patterns, signaling patterns of the signaling proteins in the active tissues. So here, these are the screenshots. So we varied this xi by dr term from 0 to 2.5. These screenshots correspond to these values in the phase diagram A, B, C, D, E, and F. So delta theta, we kept it like this is fixed by pi by 4, and this is varied. Now we can see that by varying this term, we can see from spotted light patterns to, we can go from spotted light patterns to the stripe light patterns here. And these are the phase diagrams. We quantify these patterns, the shape and size of the patterns by these phase diagrams, showing this is the number of the clusters, means the in this system total number of clusters, and in a single cluster how many delta cells. Delta cells means the red color cells. How many red color cells are there in one cluster? And the third phase diagram corresponds to the shape ratio, that is the ratio of the maximum and minimum eigenvalues. This shows the whether the system is elongated or it is symmetric. So if we combine these three phase diagrams, we can see how the means shape and size of the pattern changes with xi by dr ratio. So these are the simulation movies corresponding to the screenshots, starting from xi by dr 0 to xi by dr ratio 2.5. Now I will see the effect of motility. So how the motility, introducing the motility term, cell motility in the system affects the signaling patterns. So these are from the experiments that how the delta notch patterns are formed with the moving inside the moving tissue. So we included the motility term in both types of configurations, and then we can see how it varies with time and space. So to quantify the spatio-temporal dynamics of these patterns, we just plotted the delta-delta correlation plot. So at tau is equal to 0, we see a decaying oscillatory pattern in space, which shows the periodic delta expression with distance. And at higher values of the tau, the higher values of the time delay or tau, we see that the amplitude slowly decays, showing that the pattern diffuse in space and are not stationary. And to quantify the rearrangement time scale of the delta patterns, we plot the amplitudes of the radial distribution function corresponding to its first minima as a function of the time lag or the time delay, and fits this equation, and found that the pattern rearrangement time scale is much larger than the signaling time scale. So a new time scale emerges in the system. So the polarity, we showed that the polarity dynamics governs the shape and size of the developmental patterns. So ranging from the spot-like to stripe-like by only varying the xi by dr term. And the cell motility coupled with the cell signaling leads to dynamic patterns, as we can see in the Drosophila development. Thank you.
Okay, thank you very much. Yeah, Priya, for your presentation. So we have now time for a few questions. I remind you, as I mentioned, that you can simply indicate through the Q&A window that you want to ask a question, and then that's give you the word. So there is a first question by Rai Capral.
Okay.
Rai.
Okay, here I am. I think you can hear me now.
Now we can hear you, yes.
So I was curious just about how your work connects to the older literature on Turing instabilities giving rise to the spatial patterns in these species. So in particular, of course, there are a lot of issues concerning the nature of the morphogens, but I think like some of the experiments you quoted, in some circumstances, I think even for the striped fish that you have, the morphogens are known, and the mechanism relies on differences in the diffusion coefficients of these species. And for the specific cases, it's not simple diffusion, but in fact, it's these extended fingers that you have for the signaling molecules. So at any rate, my question is, you can certainly generate stripe and spot and moving patterns through instabilities just in the morphogens. And it seems to me that that must underlie what you're talking about. And of course, you have coupling of motion to that. So is that old Turing mechanism thrown out, or does it underlie what you have?
So there is no Turing mechanism. This is a contact-based or contact-dependent signaling here, which is known as lateral inhibition. Means this is a particular type of signaling where the two cells can only exchange the signals only when they are in contact.
Yes,
There is no diffusion term here for the morphogens.
Yeah. Well, I know what I was trying to say was that in the experiments that were done about 10 years ago, where in particular cases they've identified the signaling molecules, they are actually contact molecules, but they basically mimic a type of difference in diffusion. And in fact, just using the Turing type model with that underlying structure, they could describe the stripes and spots. So that was basically my question. So I guess you're claiming that it's completely different.
Mm-hmm.
So from these studies, it is not clear like which one is the correct mechanism or the reason behind these such type of patterns. So one can like model in both the ways and see whether which one is goes with the experiments. And
okay, thank you.
Okay. I don't know, just as a follow-up of that question then, since you claim or you show that this is a contact mechanism, is there a prediction that could then
no, it is not a prediction. It is experimental based paper. Like people have already done the experiments, like Cohen et al. They showed by the experiments that it is a contact dependent signaling takes place via such type of delta notch patterns in somatogenesis and many other like in Drosophila while during the development when motility is also there. So we just try to model those experimental papers.
Mm-hmm. Okay. I mean, I have a separate question. When you were describing the vertex model, you talk about these events where the topology changes or where one of the cells disappears because of the death. I don't know, I mean, you mentioned that because you follow up how the type of this contact interaction affects this type of rearrangements. Is something that you have followed or try to quantify as relevant in these transitions that you described? The role of topological.
So, yes, like when we put this motility term here, or suppose, sorry, when we put this motility term, it's not just the V naught that is driving the system, like V naught cell addition and the topological rearrangements also take place. So it is the combined effect of all these that the cells are in the motion.
Okay.
So if we put some motility term, this these cells will show topological rearrangements.
Okay, thank you. So there is another question by Juan David Torrenegra. This one.
Hi. In your model, each shell is formed by few particles, right? So in your model, each shell is permanent, close each other. So you connect each other through springs.
No, actually, this is a vertex model. This is a vertex model in which we start with all the hexagonal cells, means hexagonal shape cells, and it is not a particle based system. It has edges that connects two vertices, and we assume that the forces means are applied on the this vertices only, not at the cell center, or this is not a particle based model.
Okay.
So this is already a well established vertex model.
Okay. Okay, I understand. Okay. So you compare this model with a continuum model, like for example, Keller-Segal equation, or not?
Sorry, can you repeat?
Did you compare this discrete model with a continuum model like Keller-Segal equation? No.
Like people have tried to do this, but means not successfully they have done. And if one wants, like this is an open thing, one can try to do this.
Okay. Thank you very much. So I do not see any additional questions. So maybe then we get to the end of this first part of the session today. So thank you very much for joining us. And then for those register, oh sorry, there is a question that arrived. So maybe even if I'm here, okay. It's Pinaki Nayak has a question, also a question. You can stop sharing. So Pinaki, do you? No? Maybe I can rely his question. He's asking if how vortices are moving in between the tissues.
Sorry, how?
How vortices move in between the tissues.
How these vertices?
Vertices, I suppose.
Yeah. Okay. So means if we apply this. So if the force is applied on these vertices, they work on the according to this equation. These equations, these. So now the shape of the cell is decided by the shape index. That is the perimeter of the cell to the square root of area. So this will decide means which shape to take, starting from the hexagonal. If the shape index like increases, then it will go to pentagon, or it can form quadrilateral shape as well. And also it is accompanied by these topological rearrangements. So in order to change their shape, this is a very important thing, these arrangements. Otherwise, if the cells cannot arrange themselves, then means they cannot move.
Okay. Thank you. This answering this very last minute question. So as I said, just thank you for having joined us in this lectures and talks. Now we will move to the second part of this MIG-Gen. But before that, I wanted to tell you that, as I mentioned at the beginning, we look forward to see you at the next session. It will happen at the end of the month, March 25th. It will be a session about quantum Monte Carlo and the and David separately will deliver the first lecture. The whole series until June is already available. If you go into the SICAM webpage, there is the MixGen devoted page where you see the list of all the sessions and corresponding speakers. And I also wanted to take the opportunity to tell you that at the end of that page, there is a possibility to register for our mailing list if you want to receive information about this set of events and also future ones that we will organize. And we are also active on Twitter, so if you can follow with SICAM events to keep up with the latest news on our activities.